Okay, let's get started. So in this lecture, we will be talking about Bayes theorem. But before discussing Bayes theorem in detail, we will be talking about few more things, and conditional independence also we are going to discuss. Okay, so let's get started. Now carefully understand everyone. So in the previous class, I talked about marginal probability. I talked about joint probability, right? I also discussed what is conditional probability, all these things, and we also solved some questions based on these topics, right, in the previous class. And we also talked about that in uncertainty, why probabilistic model or probability approach is going to help us, right? So now I'm going to start from this one that I talked about this right in the previous class also, that we have random variables, we use random variables, and random variables can be of Boolean type. Random variables can also be of discrete type, and they can also be continuous. We can also have continuous random variable. So just a quick revision of what we discussed in the previous class, because this will set the foundation. So when I say Boolean random variables, so for example, let's talk about cavity. You know what is cavity, right? So basically, whenever we like, let's say, uh, whenever we have some toothache kind of thing, so most probably we have cavity also, right? So basically, some germs is there or something like that. So do I have a cavity in one of my teeth? So so this kind of random variable is a Boolean random variable. So either it can have a value true or it can have a value false, right? Similarly, we can have discrete random variables also, right? As I discussed in the previous lecture also, it can be finite or infinite. So for example, let's say weather. So weather is one of the discrete random variable, and it can have these possible values, which is sunny, rainy, cloudy, and snowy, right? Now, weather is equal to rain is a proposition, but this weather random variable is not a propositional random variable, right? When I ask you whether if it is raining or not, right, then you will say that yes or no, or it is raining or not. Then you will say yes, it is true, or it is false. But this weather is not a propositional or Boolean random variable. It is discrete random variable because it is having multiple values. Clear? And when we talk about discrete random variables, it has to be exhaustive and mutually exclusive, right? Similarly, we have continuous random variables also, which can be bounded or unbounded. All these things I have already discussed in the previous lecture. Now let's start from here. And this thing also I discussed, if you remember, that whenever let's say we have probability of a cavity is zero point 0.1, then if I ask you what is the probability of not a cavity, or cavity is equal to false, so obviously it is going to be 1 minus zero point 0.1, that is going to be 0.9, right? So as you know, so in case of weather also, like if I say that weather probability of weather being sunny is 0.72, probability of weather being rainy is 0.1, similarly cloudy and snowy. So if you add all these up, so that will equal to 1, right? Okay, so that means whatever possible values you can have for the random variable, if you add all of them, the sum will be equal to 1. This is very important thing, because we will use this concept in some time. Okay. Similarly, sometimes it may happen that instead of having the exact values of probability, we are having some true ratios, right? We are having some ratios like this. So now here the ratio of probability of cavity is 0.01 and probability of not of cavity is 0.09. Now if you add these two, it will not sum up to 1. So in that case, we basically normalize it, right? We use normalized constant, that is alpha, and here the alpha value is equal to 10, because if you add these two values 0.01 plus 0.09, it will be equal to 0.1, and if you multiply with 10, then the probability will become 1. Clear? The vector sum will become 1. Okay, so these are the basic things. I hope that most of you or all of you know these things well before advance, because you already have covered probability in a lot of detail, right? Hi Manjunath. Okay, clear so far? Any doubt, anyone? So you can just give me thumbs up in the reaction so that I can get to know that whether you are able to understand or not. Okay, that will really help me also to proceed. Fine, thank you. Okay, now let's see this. let's talk about the joint probability distribution. Now, this is a very important topic, joint probability distribution. What is joint probability distribution? So here, if I say, let's say you have a set of n random variables. When I say set of n random variables, for example, you can consider that weather and cavity. These are the two random variables given to you. Now, based on this slide and this slide, we know that weather is having four values. Weather is having four possible values, right? Either it can be sunny, rainy, cloudy, or snowy, correct? So weather is having four values, possible values, and cavity is having two possible values, true and false, right? Now, the joint probability distribution is so powerful that you can answer anything, right? It will give you every answer. Okay, let's see how it is going to give us the answers. Carefully see this now. So first of all, what is joint probability distribution? We know what is joint probability, yes or no? In the previous class, we have already discussed what is joint probability, right? If I have two events A and B, so A intersection B, this is my joint probability, right? Where we can have two or more events, right? So this is our joint probability, correct? Now, so what is joint probability distribution? So this is for a set of n random variables. When I say n random variables, so in this example, we are considering that weather and cavity, these are the two random variables that we have. Okay. And it gives the probability of every atomic event on those variables. So in the joint probability distribution, or you can say a table, joint distribution table, you will be having the values of all the or every atomic event. When I say every atomic event, that means what? That means whether is sunny or not. So for sunny also you will be having the value, for not sunny also you will be having the value. Similarly for rain also you will be having the probability value in that particular distribution. Similarly for cloudy also, snowy also. And if I talk about the other random variable, which is cavity, so it is also going to have its value present in that distribution. Okay. So every sample point will be covered. So joint, that's why I was saying that joint probability distribution can answer anything, any question. So if you say that, let's, for example, if I ask you a simple thing, you all have to answer based on this table. If I ask you, what is the probability of weather being sunny and cavity is true? Can you answer, anyone? What is the probability of weather being sunny and cavity is true? So answer is simple, that is going to be 0.144. Yes or no? Is this clear? Similarly, if I say, what is the probability of weather being not sunny, or let's say weather being sunny, cavity is equal to false, or cavity or not of cavity, then you will say it is simply 0.576, right? So joint probability distribution is very powerful, right? It can answer anything. You just need the complete distribution. Okay, you will understand in some time why I'm talking about this joint probability distribution, how we are going to use it in predicting the uncertainty. Okay, so you are going to understand in some time. Okay, and in the upcoming lectures also. Let's proceed further. So here, let's consider this example only. So it is an n-dimensional matrix. So you know weather is having four possible values, cavity is having two possible values. So matrix is going to be 4 by 2. That means the table size would be 4 into 2. That is total 8 values will be there in this matrix. Correct. Now the entries contain probabilities for all possible combinations, as I told you just now. Fine. Now carefully read this line. This is very important line. Every question about a domain can be answered by the joint probability distribution. Why? What is the reason? Because every event is a sum of sample points. If you add all these values, now carefully understand this. If you add all these 8 values, they will sum up to 1. Are you getting this? That means the probability is distributed over all these values, or you can say over all these matrix. So if you add all these 8 values, it will be equal to 1. Is this clear so far? Do you have any doubt? Yes, no? All clear, crystal clear? Shall we proceed now? Okay. So I'm going very slow so that you can understand each and everything clearly. Even if you know it before, well and good for you. But if you don't know, it will be a really, I can say you will be able to understand very well. Okay, fine. So now, when we talk about conditional probability, so what is conditional probability? Carefully see this. If I'm writing probability of, let's say, A given B, that means what is the probability of A when B has already occurred, when B is already given. So we know this, it is equal to P of A intersection B divided by P of B. We know this, we all know this, right? Now, what is this actually? If you carefully observe this, what is this actually? This one. So this is posterior. This is posterior. We will be talking about, this is conditional probability. Basically, it is nothing but posterior probability. So we have something called as prior probability and we have something called as posterior probability. What is the difference between these two? Prior, what do you mean by prior? That means you know something in advance, right? You know something in advance. So if I say, let's say, maybe if I say, let's say P of E, can I say this is my prior probability? Yes or no? Do you agree? Can I say this is my prior probability? Why I'm saying this is my prior probability? Because this is unconditional. There is no condition attached to it. This is unconditional probability. We are just finding out what is the probability of this event E. So that's why we are calling it as prior probability. But what about this one? P, probability of A given B. So now we know something also, right? Apart from finding this probability, we also know something in advance, right? Some event has already happened. So we call this as posterior probability. We call this as posterior probability, which is, we can say this is conditional. Conditional probability, this one is our posterior probability. Understood? Okay. So now carefully see this. So when I say, let's read the definition also. So prior or unconditional probability refers to degree of belief. That means simply the probability in the absence of any other information. That means in advance, we don't have any other information. We are just interested in finding out the probability of certain event. So that is our prior probability. And what is posterior? That is conditional probability, refers to the degree of belief when we have some information in advance. And we call that some information which we have already, we call that as evidence. We call that as evidence. So we have some evidence, we have certain information in advance, and then we are finding a probability of an event, right? So similarly here, we have this information already given to us. It is already given to us that this event has already occurred, right? And then we are trying to find out the probability of this event. Correct? So this is our posterior probability. Correct. Now there are some examples given here. So basically this is very simple, right? Consider drawing straws from a set of 1 long and 4 short straws. So let's say in a bag, you have 1 long straw and 4 short straw, right? Now what is the probability of long? Now you don't know any other information about this apart from this, right? Whether any other event has happened or not. So can I say this is my prior probability? Do you agree or not, everyone? This is my prior probability. Probability of long is 0.2. How we are finding it 0.2? Because it is nothing but, you can say probability of long is nothing but 1 by 1 plus 4. That means the total sample space. So it is 1 by 5, which is nothing but 0.2, right? Simple stuff. Similarly, now if I say this one, probability of long we are finding out, and it is given that short has already occurred, or we have already found out in the previous attempt, we have already drawn the short straw. So what will be the probability in that case? Then we know if short has already drawn in the previous attempt, now what is the probability of long? If short has already drawn, can I say now we have 3 short straws in the bag? So it is going to be 1 by 1 plus 3. That is 1 by 4, which is nothing but 0.25. Is this clear? So these are the examples. You can consider these examples. Any doubt, anyone? Similarly, let's consider this third example also. Probability of long, given that the long straw you have already drawn in the previous attempt. If you have drawn the long straw already in the previous attempt, in the bag, you don't have any other long straw. Yes or no? Because only 1 long straw was there. So the probability of that will be 0. Is this clear? Can you repeat this again, Sneha? Okay. So basically, okay. So when I say probability of long, let me explain you here. This is simple, but okay, let me explain this. Probability of long given short. Now, what does this indicate? That this short straw you have already, this is given, right? That is the meaning of conditional probability. This is already given to us, that we have already drawn the short straw in the previous attempt. Now we are finding the probability of long. So if you have one long straw and four short straws, if you have already drawn one short straw, so now you have only three in the bag. So what will be the probability of long? That is going to be 1 plus divided by 1 plus 3. That is going to be 1 by 4, which is nothing but 0.25. Similarly, you can find for other as well. Is this clear? This one, is it clear? This, do you have any doubt in this one? Anyone? Just tell me how this is 1 by 3. Clear to all? Because here it says probability of long, it is given that you have already drawn two short straws in the previous attempts. So now in the bag you have how many remaining? 2. So 1 divided by 1 plus 2, that is going to be 1 by 3. So I hope these things are crystal clear to you, right? Now we can proceed. So these two terms, it is clear to you that what is prior probability, which is unconditional, and what is posterior probability, which is conditional. Let's proceed now. Okay. So now we are going to discuss some very interesting stuff. So conditional probability, let's continue here. Now let's consider these examples. So let's say we are considering example of cavity, and basically this is an example of dentist. This is a famous example of dentist problem. So we are trying to find out the probability of cavity given toothache, right? So let's say it is given to you. It is given to you that we want to find out what is the probability of cavity given toothache. That means it is given to you that toothache is there. Okay, it is given to you that toothache is there. Okay, that means you have pain in your tooth. Okay, so toothache is there. Now you are trying to find out the cavity. So it is given that it is 0.8. So what does it indicates? What does it means? It means the probability of cavity given that toothache is all we know. This is we understood, but this line is also very important. Carefully read this. But it does not mean if toothache, then 80% chance of cavity is there. All of you know what is cavity, right? Or like daat mein keeda lagna, we call it as cavity, right? Simple. Okay, fine. Right. So yeah, so it does not mean if toothache is there, then 80% chance of cavity. Are you able to understand these two statements? What it looks similar, but it is different. Carefully understand again, carefully read it again. What is given to us? Probability of cavity given that toothache is all we know. So we know it that toothache is there. That's all we know. Other things we don't know about it, right? So, but it does not mean that if toothache is there, then 80% chance of cavity. So that is not the meaning of the statement. Are you able to differentiate between these two statements or not? Carefully read it. I'm giving you a few seconds. Carefully read it. If anyone is having doubt in this, please ask. Clear to all? Okay. Good. Great. Okay. So let's proceed now. Suppose we get more evidence. Now let's say we get more evidence. Now what else is given? Cavity is also given. Okay. Now it is given to us that cavity has already happened. Now it's very simple. If cavity has already happened, if we have more evidence, then what will be the probability of cavity? Obviously it is going to be 1. Because we are trying to find out the probability of one event, and that event has already happened. So can I say the probability will be 1 only? Yes or no? Simple stuff. Okay. So now let's proceed. Now, sometimes we may have some irrelevant evidence also. Now carefully see this. New evidence that we are adding, sometimes it may be irrelevant, right? So for example, if it is given to you, probability of cavity given toothache has occurred and weather is sunny. Now, don't you think that, this evidence, this particular evidence that weather is sunny is irrelevant to this cavity problem? Like, hypothetically, or in the parallel universe, you may think that, not in the parallel universe, but hypothetically, you can think that weather is too sunny and the temperature is very high, and somehow the temperature is affecting your teeth also, and you are having cavity. So hypothetically, it is, you can say it is possible, right? Somehow it is possible, but logically, intuitively, if you ask, right, so then you can clearly say that weather being sunny and you are having the cavity, they are not relevant, right? In a real world, a logical world, basically, we can say that this is not relevant. So if it is not relevant, we can simply avoid this. We can simply avoid this event. So now it will become what? Probability of cavity given toothache only, right? So that is equal to 0.8 only. Clear? Okay. So, and these things I already explained it to you, that we have this, you will understand in some time. So basically, these are just two element vectors as given, cavity or not cavity, toothache or not toothache. So these things are given. Okay, let's proceed now. Now, conditional probability, we have already discussed. Definition of conditional probability, it is clear to us. So one more thing I want to explain here before proceeding. If I talk about conditional probabilities, it is, let's say, probability of event A given B is equal to probability of A intersection B divided by probability of B. Now, using the multiplication rule, I can write like this. Using multiplication rule, I can write like this, that probability of A intersection B is nothing but probability of A given B. Correct? We can write like this. And this is what it is given here also. Okay. And one more thing we can write. Now carefully see this. We are basically going to discuss the Bayes theorem here in short. So in short, you can say. So this is given. This is what you have written. Now I can write like this also. If I say probability of B given A, can I say it is B intersection A divided by probability of A? Again, conditional probability, right? Now this thing and this thing, can I say it is same? Because ultimately you are finding the joint probability of event A and B. So can I write like this? Similarly, here also you can write like this, that B intersection A is nothing but probability of A into probability of B given A. Now this equation, let's say 1, equation 2. Now what can I write using these two equations? Now carefully see this. Can I write like this? Probability of A given B is nothing but probability of B given A, probability of A divided by probability of B. Is this clear to all of you? This is what? This is your Bayes theorem. Yes or no, everyone? This is your Bayes theorem. Correct? Any doubt, anyone so far? Anyone having doubt how we are getting this equation? Basically, this value and this value we have equated. So now we have this, and just we have rearranged it. Okay. So this is what we are getting. Okay. Come back here. Now, so this general version holds for entire probability distribution. For example, if I say probability of weather and cavity. So when I write weather comma cavity, that means we are talking about weather and cavity. So joint probability. Okay. This is a joint probability we are finding. So we can write like this, probability of weather given cavity into probability of cavity, right? Using this one we can write. Okay. So now let's proceed. And I hope you know what is chain rule also. So we are discussing few things, and now we are going to combine all these things to understand the major problem. Okay. So what is chain rule? Chain rule is also very simple. So let me discuss that also. So if I'm writing this, let's say x1 and x2. So I can simply write it like this. It is probability of x1 into probability of x1 given x2. Using conditional probability and multiplication rule, we can write like this. Similarly, if I say probability of x1 comma x2 comma x3, because we can have 2 or more events, right? So can I write like this: probability of x1 into probability of x1 given x2, correct? Similarly, what else we can write? What else we can write? So basically we want this thing. So I can also write like this, that it is going to be probability of so here, yeah, so now we can have these two things. So we can write probability of x3 given x1 comma x2, right? And then we can have finally probability of x3. Let me just see here. Okay, so if we have 3 events only, let's say we have 3 events only. Fine. If we have 3 events only, so we can write like this, yes or no? Any doubt in this? See, first consider this one. When we have only 2 events, so we can write probability of x1 into probability of x1 given x2 using conditional probability and multiplication rule, right? This comma is nothing but intersection. When we have 3, then we can write probability of x1 into probability of x1 given x2 into probability of x3 given x1 x2. Similarly, you can continue for 4 events, 5 events, and so on. Okay, is this clear? Any doubt, anyone in this? This is what, this is your, using chain rule you are getting this. Oh, sorry. Yeah, yes, Gurdeep. So it should be x2 and x1. Yes, I'm sorry. My mistake. So this is x2 given x1. And here also it is x2 given x1. Yes, now it is correct. Is this clear? Okay, so this is our chain rule. This is our chain rule. Now let's proceed. Now let's see carefully. Now we are going to talk about the main thing here. Inference by enumeration. When I say what is enumeration, enumeration means you are enumerating over all possible values that you have in the joint distribution. This joint probability distribution, as I told you, that can answer anything related to some domain. Okay, so let's see how it is going to help us. So let's understand this dentist domain problem only. So what is the probability of a cavity given toothache? How we can find it out? Probability of a cavity given the prob catches. Prob catches means, that means some microbes are there. Okay, so when you have cavity, then there is a chance, right? You are having microbes present in your tooth, right? Clear? So this is what prob catches means. That means you are able to catch the microbes. Now carefully see this. So we first of all we start with the joint distribution. So we are considering all the possibility in the joint distribution. We have how many random variables we have here now? By seeing this particular joint distribution, can you tell me how many random variables we have? Anyone? Three random variables we have, exactly. One is toothache, second one is catch, and third one is cavity. Is this clear to all of you? Any doubt in this? Three random variables we have here. Okay. Now, can I say all these 3 random variables are having 2 possible values? Like for toothache also you can have 2 possible values. For catch also you can have 2 possible values. For cavity also you can have 2 possible values, right? Okay. Now let's say this. So if I ask you a simple question, let's see here. If I say, what is the probability of toothache? Just by seeing this joint distribution, if I ask you what is the probability of toothache, can you tell me what are the values that you are going to add to find the probability of toothache? Can I say that I am going to add these 4 values? Do you agree or not? Correct. These 4 values I'm going to add just to find the probability of toothache, because this column represents all the probabilities related to toothache. Similarly, if I ask you what is the probability of not a toothache, so either you can add all these or you can add these and you can subtract. Correct? Okay. Now what next? Now carefully see this. If I ask you again a simple question, what is the probability? What is the probability of cavity given catch? What is the probability of cavity given catch? So we are finding out the probability of cavity. It is given that catch is there. So can I say I'm going to add these two values? Yes, that is correct. Absolutely correct. Because we are finding out the probability of cavity and it is already given that catch is there. That means we have catch the microbes, right? So catch is there. So catch is there in these two columns, right? So this value and this value, and this belongs to cavity. So basically we are going to add these two values. So are you able to understand that using joint probability distribution, you can answer anything related to a domain? Is this point clear or not to everyone? Okay. Okay, good. That's good. So this is how we are finding out. This is how we are finding out. And one more thing that I told you already, that if you add all these values, they will sum up to 1. They will sum up to 1. Yes, why not the sum of probability in toothache, okay, and not toothache as 1 in cavity? Because see, Abhas, here you have to consider all the random variables, right? So here you have random variable cavity, catch, and toothache, right? So when you say sum of probability in toothache, that means these 4 values. If you add these 4 values, so you are also considering the value of not cavity, right? Because you are simply saying what is the probability of toothache. Now, when you are simply saying what is the probability of toothache, it may be possible that you have cavity or not cavity, right? Sometimes, you don't have cavity, but still you have toothache. Similarly, sometimes you have catch, and it may also happen that you don't have catch. That means there are no microbes present in your, mouth, right? So we are going to consider these 4 values to find out the probability of toothache. I hope I answered your doubt. Okay, good, fine. So let's proceed now. So I also told you that if you add all these 8 values, they will sum up to 1, because that is the point of joint probability distribution. Okay, so it will sum up to 1. So this thing you understood so far. Okay, now if I ask you probability of cavity, marginal probability is not 1 here, obviously. Simple probability is not 1 here. Okay, yes. Okay, so now carefully see this. If I say probability of cavity or toothache, then what are the values you are going to add? Just don't see the values here, just see the table. I want all of you to just see the table here and tell me, or just find out probability of cavity given probability of cavity or toothache. So probability of cavity or toothache, that means cavity can be there. Either cavity is there, that means all these values can come, or toothache, that means this column. So all these 4 values will come. Now, you know this formula also, right? If I say, carefully observe here, if I say probability of A union B or B, can I say it is nothing but P of A plus P of B minus P of A intersection B? Do you agree or not, everyone? We know this already, correct? So if I'm finding this probability of cavity or toothache, can I say that if you add, see, toothache means these 4 values, you know this, toothache means these 4 values, correct? And cavity means these 4 values. So by joint probability distribution also you can find out that we need to add these 4 values and these 2 values, correct? But let's say this joint probability distribution is not there, but just the values are given to you, but not in the table, in the tabular form. Then what you will do, you will find the probability of A, let's say here probability of cavity. So you will find this thing plus probability of B, that means probability of this, right? And you are subtracting intersection part, so you are subtracting common part. If you are adding it twice, carefully observe here, don't you think that you are adding these 2 values twice? Everyone, I'm asking this to everyone, don't you think that you are adding these 2 values twice? Yes or no? Why you are adding these 2 values twice? Because these are common. So that is the reason why we subtract A intersection B out of this. So if you see the calculation here, you are not adding these two values 0.108, 0.12 twice. I hope this is also clear to all of you. Okay, fine. So now we can proceed further. And similarly, we can answer this also, that probability of not cavity given toothache. So probability of not cavity, it is already given that toothache has occurred. So toothache has occurred, that means all these values, and finding out not of cavity, so that means these values we are talking about. Is this clear? So it is nothing but probability of not cavity and toothache divided by probability of toothache. So this is how you can find it out. Is this clear so far? Any doubt, anyone? If you have any doubt, please ask. Crystal clear? Shall we proceed now? Okay, fine. Similarly, these things also you can just see. Okay, now let's see carefully. There are some issues. There are some issues in this joint probability. You have understood that joint probability distribution is very powerful and it is very useful also. But don't you think that finding all the possible random variables for a certain event or for a certain domain, finding all the, see, if I talk about just this dentist problem, right? So apart from toothache, catch, don't you think there can be many more random variables possible? Yes or no? There can be more evidence possible that we are not even considering here. There can be some hidden variables also. Yes, we can have some hidden variables also, right? So let's say first problem is finding out all the possible hidden variables or all the possible random variables. The next thing is, let's say you have found out all the possible random variables. Now getting the joint probability distribution of all those random variables, don't you think that will take, the time complexity will be more and space complexity will be huge? Because if you are making a table, that will definitely take a lot of space, right? And similarly, finding out that also will take time complexity will be very high. So if we have, let's consider the random variable is n. Let's say you have n random variables and d is the largest arity. What does it mean? So let's consider with the example, d means possible values of a random variable. So we are considering that every random variable is having d possible values. Let's say in case of cavity, you have two possible values, true or false. In case of toothache, you have two possible values, true or false, right? Similarly, if I have n random variables and if d is the largest arity that you can have, that means the largest maximum values it can have. So the worst time case complexity will be order of d raised to the power n. Yes or no? Why I'm saying so? Because you need to find all the possible values of each random variable. Yes. So this is going to be the time complexity, worst time complexity. Similarly, finding out all the values and then storing all the values in the entire joint distribution. Can I say that will also take this one? Because if you consider this example also, how many values you have? 8 values you have. Why? Because toothache is having 2 values, catch is having 2 values, cavity is having 2 values. So 2 into 2 into 2, 8 values you have. So space complexity is also very huge, right? That is exponential. Worst time complexity is also exponential. So far after this discussion, we have understood that joint probability distribution is very useful, very powerful, because it can answer anything. But finding out it, that takes a lot of time, and store it, that also that consumes a lot of space. So there are some disadvantages also, right? And one more thing is how to find the number of these many entries. That is also a problem. Okay, so now how to tackle this problem? How can we reduce it? Now the question comes that we want to use joint probability distribution, but can we reduce this time complexity or maybe space complexity somehow, that we don't have to compute this much, that we don't have to store this much, and still we can use the joint probability distribution? So in order to reduce it, now comes the next concept, that is independence. So what is independence? We know this thing, that random variables a and b are independent if and only if. So you know this, right? If I'm writing p of a given b, And if I say A and B are independent, so you know this, that it is equal to conditional probability P of A intersection B divided by P of B. And if they are independent, you know this term will be equal to what? P of A and P of B divided by P of P. So this will cancel out and finally you are going to get P of A. So this is what you are getting. Is this clear? Similarly, you can say P of B given A will be P of B. Is this clear? Because they are independent. So if they are independent, then we can say this will hold. Clear? So this is the concept of independence, but how we are going to use it, you will understand in some time. Now, carefully see this. This is very interesting. So you understood what is independence. Okay. Now just see this one, just this part. I want all of you to just focus on this circle. What do you have inside this circle? You have cavity, you have toothache, you have catch, you have weather. Can I say, if you try to decompose it, can I say weather is kind of independent here related to these things? Yes or no? Weather is independent. So what we have done, we have decomposed into this thing and weather separately. Now let's say before decomposition, that means when I'm talking about this part, can you tell me how many entries would be there? If I consider all these random variables, can you tell me how many entries would be there in my joint probability distribution table? Anyone? $32. Sumit, weather is having, see, weather can have 4 values, right? We have already considered, right? Sunny, cloudy, rainy, and snowy. So weather can have 4 values, right? And all these cavity, toothache, and catch, they can have 2 possible values. So 2 into 2 into 2 into 4. So that is going to be 32. So carefully say this, that is going to be 32 entries. So the first thing is, first of all, what you are trying to do, you are first of all trying to separate the random variables which are completely independent. There is no dependency at all. So can I say that you have reduced 32 entries? Earlier you were having, initially you are having 32 entries in the joint probability distribution. By the concept of this independence, you have reduced it, you have made it separately. Now you have how many? 2 into 2 into 2, that is for cavity, toothache, and catch, plus 4 values for this one. That is, now you have 12 entries. So can I say somehow I have reduced it? How we have reduced it? By separately, by whatever random variable that is independent, we have removed it and we have kept that separately. Is this clear? So far we have reduced from 32 to 12. Is this clear? Any doubt, anyone? Okay. Okay. Now, so what we understood here, that absolute independence is powerful. Like in this case, this is absolute independence, because weather is logically also, weather is not at all related to these random variables, right? So this is kind of absolute independence. So absolute independence is definitely powerful, because from 32 you are, just by eliminating one random variable, it is now 12. You can see how significant you have done, how significantly you have reduced the number of entries. So absolute independence is definitely powerful, but it is rare, because it is not always that, majority of the random variables will be independent. Because dentistry, the example we are considering, dentist problem, dentistry is a large field with hundreds of variables. Is it so that most of the variables are independent? No. So none of which are independent, then what to do? If we, now we are stuck again, right? We started with joint probability distribution. Now we are at independence, absolute independence, but now again we are stuck. Can you see the problem? Can you see understand the flow? Now we are again stuck, because not all random variables will be completely independent. Now what to do? Now how we can further reduce it? Now comes the concept of conditional independence. Okay. How many of you know what is conditional independence? One, two. Even if you don't know, it's there is no need to worry. I will be explaining you each and everything. Just I'm asking, I'm curious to know this, that how many of you know what is conditional independence? Independence, this topic is everybody know, right? Independent events and all. But conditional independence, that we need to discuss now. Okay. Are you finding it interesting or not? Right? I hope you're finding it interesting. Now let's proceed. Okay. So what to do now? Now we are going to talk about something called as conditional independence. That means independence is there, but it is based on conditions. Okay. So let's see what I'm talking about. Carefully see this. Consider probability of two things. Now weather is gone, right? Weather is absolute independent, so we have removed it. Don't consider it now. Now we are just focusing on these three things. Carefully understand it. This is very, very important. Consider probability of toothache and cavity and catch. Can you tell me how many parameters or how many entries I have in the table, or I need to maintain in the table quickly for these three random variables? You will say, sir, answer will be 8, right? 2 into 2 into 2. So answer will be 8. But can I say that I can further reduce it 2 raised to power 3 minus 1? That means 7 entries I need to maintain. How many of you understood this thing? Let's say we have just these three random variables. You understood that toothache can have 2 possible values, cavity can have 2 possible values, catch can have 2 possible values, 2 into 2 into 2, that means 8 values. Removing the empty case. What empty case? No, that is not correct. Empty case we are not going to consider, right, Sumit? If nothing is there, then anybody else? Why I'm subtracting this? Why I need to just store 7 entries? This is very, what do I say? This is very logical, and you already know this, right? Once I'm going to tell you, you will be saying, oh yeah, that is the reason. Okay, let me tell you this. So you know this. If I'm going to make a joint probability distribution table, I will be having 8 values. But don't you think that one value you can eliminate? Why? Because the sum of the remaining values will be what? The remaining value will be 1 minus sum of all. I told you that in the joint probability distribution, sum of all the probabilities is equal to 1, right? So can we say that you just need to maintain the 7 entries, because the remaining 8th entry, you can find it anyway by adding these 7 entries and subtracting from 1. So we are just going to have 7 entries now. Is this clear? Okay. Now if I ask you a simple thing here, what is the probability of, can anybody answer here? What is the probability of catch given toothache, cavity? I mean, I'm not asking the number, but what it should be equal to. Okay, let me frame it differently. That way you will be able to understand what I'm asking to you. Carefully understand this. When I say probability of catch given toothache, cavity. Okay, so 5 entries. Okay, let's see here. Carefully understand this. This is very interesting. You will also find it interesting. Carefully see this. So as of now, we are having just 7 entries in the distribution table. Okay. When I say probability of catch given toothache, cavity. Now, carefully understand this. Can I say if it is given to you that you have cavity? Okay. That is correct. Yeah, that way you can write. That is correct. Using just conditional probability. Yeah, that is correct. That you can write. Okay. Now carefully see this. What I want to say here. What is given to you? That you have toothache and cavity is also there. Fine. When you have cavity, when you have toothache and cavity, then you are finding what is the probability of catching the microbe, right? catching the bacteria, you can say, or microbe, you can say. That you need to find out. But don't you think when once you have cavity, then this having this toothache is irrelevant? Think about it. Once you know that you have cavity, it is given to you that you have cavity, catching the catching the microbe does not depend on this toothache. Yes or no? Because if you have cavity, yes, we can eliminate it, right? We can eliminate it. That's what I'm saying. So if you already know that you have cavity, definitely catch will be there, right? Or catch is there or not, we are not talking about it, but we can clearly say that toothache is irrelevant, because toothache, okay, so you can also say that irrespective of pain, there are germs in the cavity. Yes, that's what I want to say. So you have understood, right? So we can say that toothache is irrelevant, some kind of irrelevant, we can say. So we can eliminate it. So if we can eliminate it, I can write like this. I can clearly write like this, that this will be equivalent to just this probability of catch given cavity. Understood this thing? Okay. Now, one more thing. So some of you can have doubt. So sir, like toothache is independent or what? Right? If you are completely eliminating it, is it independent? Isn't it independent? So now let me make it clear for you. Consider, let me write it here. Probability of catch, carefully see this. Why it is conditional independence, most of the students, they don't understand. Okay, so let me make it clear for you. Probability of catch given toothache. Can you write this? Now my question is this. Can you write this like probability of catch? Just tell me yes or no. What do you think? Whatever you think, just tell me. Can we write like this? Okay, Chandana is saying no, we cannot write. Anyone else who thinks that we can write like this? Because toothache is, toothache is not playing any part in the catch. Because here we have eliminated toothache, right? What about this one? Yes. Are toothache and catch independent? That's what I'm asking to you. What do you think? Like see, here I have removed toothache, right? Here I have removed toothache because what I said to you, that it is already given to you that, yes, exactly. It is already given to you that cavity is there. Cavity has already occurred, right? And then probability of getting a catch or getting a microbe, in that case, toothache is not playing any important role, right? So we can eliminate it. But now here, if I say this, so this is incorrect. This is incorrect. Why? Let me explain this to you. See, if probability of toothache, if you have toothache, right? Can I say toothache probability of high probability of toothache will increase the probability of cavity? Do you understand this or not? Yes or no? If you have high probability of toothache, can I say you have high probability of cavity? If you have high probability of cavity, can I say you have high probability of catch also? So now, are you able to understand that directly it is not dependent, but yes, somehow it is influencing. Somehow toothache is influencing what? Probability of cavity, and probability of cavity is influencing probability of catch. That is the reason why we cannot write like this. This is incorrect. But here it is correct. Why? Because it is given to us already that cavity is there. Now I don't need whether toothache is there or not, right? Catch will be, we can find the probability of catch. Is this concept clear to you? This is the concept of conditional independence. Do you have any doubt here? Let me write this for you if later on, if you revise. So probability of, basically probability of toothache, if it is high, it is going to influence probability of cavity. This will become high, and this will influence the probability of catch. So this will also become high. So somehow it is dependent. That is why I'm saying it is not absolute independent, right? This is conditional independence. Now I hope you are able to understand why this is conditional independence, because due to this condition, due to this cavity condition, now toothache and catch, they become conditional independent. Crystal clear? Okay, great. Let's proceed. So I can also say similarly, this thing you understood, same independence hold for this one also. Like not of cavity, if cavity is not there, then catching a microbe, that again, that does not have any, you can say that is conditionally independence of toothache. So similarly, we can write this statement as well. Clear? Okay. So we can clearly say, we can conclude that catch is conditionally independent of toothache given cavity. This is important, given cavity. So this thing we can easily write it down. Okay. Now, so initially we started with 7 entries, right? If we consider this, we started with 7 entries in the joint distribution table. Now we need only 5 entries in the joint distribution table. Think about it. Now this is our full joint distribution that we are going to write out using chain rule. Okay. We will answer, or I want you to think why we need only 5 entries now. Why not 7? Initially entries, right? But now we need only 5 entries. I will answer also. But I want to. So now our full joint distribution. So using chain rule, I can write like this: the probability of toothache, catch, and cavity will become what? See, you can use any order, right? To write joint distribution, you can use any order. Okay, you can start with catch, you can start with cavity, you can start with toothache. Ultimately, we just want to write the full joint distribution. So probability of toothache, catch, cavity, we can write like probability of toothache given catch, comma, cavity, right? Catch and cavity. Probability of catch, comma, cavity. So this thing we can write. Again, the same thing, multiplication rule we are using, nothing else. Further, this thing, probability of catch and cavity, I can write like this: probability of catch given cavity into probability of cavity. Again, the same multiplication rule. Yes or no? Able to understand, everyone? Okay. Now, you know that catch and toothache, when cavity is given, then catch and toothache, they become conditionally independent. So I can write simply like this: yes or no? That probability of toothache given cavity into probability of catch given cavity into probability of cavity. So now I can say this is equivalent to this one. Okay. Now the point is, now, is this clear so far, everyone? Yes, no? Any doubt here? You can let me know if you have any doubt. Just take a look at it, and I'm giving you some time. Let's take 1 minute if you want, but just let me know whether these steps are clear or not. Any doubt, anyone? If it is clear, just give me thumbs up in the reactions. Shall we proceed now? Okay, good. Okay, so we understood that in previously I was getting 7 entries. But now, as I told you, that now only 5 entries are needed. Okay, so now we are going to talk about it, why 5 entries are needed in this table. Now my full joint distribution Earlier it needs 7 entries, but now we have this thing, right? Why we need 5 entries or 5 parameters, you can say, in the table. Okay, can anybody tell me how many entries or how many parameters would be there for this particular term, probability of cavity? Think about it and let me know how many entries I need, or how many parameters you can say, or how many entries you can say in the joint distribution table. Okay, Manjunath is saying 2. Anyone else? Just for this probability of cavity. Think about it. Sumit is saying 1. Okay. Anyone else? Any answers? See, I want minimum. I want minimum always. Okay, so the correct answer is 1. The correct answer is 1. See, for probability of, yes, for probability of, exactly, that is correct. For probability of cavity, I just need to maintain one entry. Let's say I'm maintaining the entry for probability of cavity. Then probability of not cavity, do I really need to store this value? Tell me everyone. Do I really need to store this value? No, because if I have the probability of cavity, I can find probability of not cavity by subtracting from 1. If I have this one entry, 1 minus this, whatever value is this, I can get the value for this one also. I'm talking about the table, Chandana. I'm talking about the joint distribution table. Okay, because there we store the values, right? Yes or true or false, both the values. So basically I'm trying to store the minimum values, right? I want to reduce the space complexity as well as time complexity. Okay, so now I can say I just need to have one entry for probability of cavity. Can anybody tell me how many entries I need for this one? Let's see how many of you can answer this. Probability of catch given cavity. Sumit is saying 3. Okay. Yes. Anyone else? Think about it. I'm giving you some time. You don't have to answer in a hurry. We have a lot of time. You have to ask these questions to yourself now. Like, if I have probability of catch given cavity, how many entries do I really need for just for this term? Madhav is saying 2. Okay. Yes, Abhas, Manjunath, Chandana, and everyone. What do you think? Okay, let's consider this now. What do we have? Probability of catch given cavity. Yes or no? This is what we have. Okay, carefully say this. If I'm considering this thing, and if I want to find out what will be the values in the joint distribution table, what I have to store actually. So can I say this thing, I can write like this? What are all the possibilities? You will say, sir, the possibilities are like this, that you can have catch given cavity. This is one possibility. You can have not catch given cavity. Correct. What else? What else? You will say, sir, we can also have this, that not cavity. If not cavity is there, then what is the probability of catch? And not cavity is there, then what is the probability of not catch? Now, can you tell me what sums up to 1? You have these 4 possibilities. Can you tell me what sums up to 1? Which 2 values, which 3 values, or if I add 4 values, then I am going to get 1? What do you think? Nothing. Are you sure, Manjunath? Don't you think if I add these 2 values, that will sum up to 1? Yes or no? Because it is given to you that cavity is there. Now, having a catch or not, if you add these 2 values, definitely they will sum up to 1. If you are having any doubt, let's say you have doubt, okay? So if you are having doubt, just in your rough notebook, make a table of 2 by 2, make a table of 2 by 2 and consider that cavity is there. Now see whether catch is there or not. So you will find that these two values will sum up to 1 now. Okay, if only this information you have that cavity is there, then catch and not catch will sum up to 1. Similarly, if you have not of cavity, then catch or not catch, this will also sum up to 1. So for this particular value, how many entries do you need? Can I say 2 entries? One for this one for this one. Are you able to understand? Again, I'm repeating, these two values will sum up to 1. These two values will sum up to 1. So ultimately, you just need to store 2 entries. Now it's up to you whether you store this entry and this entry, because this one you can get from 1 minus this particular probability. This one you can get from 1 minus this probability, you can get this one. Are you getting this or not? Yes or no? So can I say, now it's up to you. Out of these two, you can store any one. Out of these two, you can store any one. You just need 2 entries for this one. In the joint distribution table, I'm saying, in the joint distribution table. Is this clear? Any doubt, anyone? So here you need 2 entries. Now I hope you can answer for this one easily. How many entries do I need for this one? Probability of toothache given cavity. How many entries? Again, it is similar that 2 entries you need. So can I say you need just 5 entries now in the table? That is 2 plus 2 plus 1. 5 entries. So do you see the difference? Do you see the usage of conditional independence? We started just from the joint distribution. Then we use the probability of independence. And then we are using the property of conditional independence. And then we are able to further reduce it. Because ultimately we knew it, that joint distribution table that we need at any cost. We need it at any cost because that can answer anything. Any uncertainty that can answer. If you have all the probabilities, you can answer any uncertainty. Are you able to understand this thing or not? Correct? So, but the problem was space and time. So we reduce the entries using these concepts. Is this clear? Any doubt? So then we have the concept of Bayes theorem. That we have already used it, but just I'm revising it again. So carefully see this. Okay, so one more thing I wanted to discuss here. Okay, so let me discuss it here only. Just let me add one slide. So we had 3 things here, right? We have cavity, we have toothache, we have catch. Now, if I ask you what influences what, can you tell me? Or what random variable depends on which random variable? You can tell me what arrow should I make? Should I make an arrow from toothache to cavity? Should I make arrow from toothache to catch? Should I make arrow from catch to cavity? Because if you are making an arrow from one random variable to another random variable, that means they are dependent. So can I say, okay, let me tell you, can I say that we can have this kind of arrow? Yes or no? That this is a cause. Basically, cavity is what? Cavity is a cause. And this toothache is an effect. Yes or no? Cavity is a cause and toothache is an effect, right? So can I say that toothache influences cavity? So can I say that this toothache is dependent? Basically, there is an arrow from cavity to toothache. Can I say there is a dependency? There's some relation between these two. Correct. Similarly, this catch also plays a role. Similarly, this catch also plays a role for cavity. But what about this toothache and catch? That we have already seen that they are conditional independence. If cavity is given to you, now carefully understand this. If cavity is given to you, can I say that toothache and catch is conditional independence? That we have already seen. Yes or no? That is the reason why there is no error between why there is no arrow between them. Is this clear? So this is a cause and these are the effects. And the diagram that you are seeing on your slide, this graph that you can see here, this network that you can see here, this is the graph. This is the Bayesian network that we are going to talk about in the next class. And from that class, our uncertainty will actually start. The topic reasoning under uncertainty will actually start. This is the Bayesian network. And this Bayesian network can tell us a lot of things that we will be discussing in the upcoming lecture. Is this clear so far? Do you have any doubt? Now, can you see this, that the concept of joint probability distribution, probability, then Bayes theorem, then conditional probability also included, right? Conditional independence also included. All these concepts are basically concluded or used to build the concept of Bayesian network. That will really help us to to have or to find out the probabilities when there is uncertainty present. You will understand that in some time. Don't worry about it as of now. Is this clear? So there was one person who used all these concepts of probability, mainly the Bayes theorem and the conditional independence. If you carefully observe, these two concepts are mainly used. Bayes theorem and conditional independence, these two concepts, he used it to build the probabilistic models. And that person got awarded the Nobel Prize in computer science. Basically, in computer science, the Nobel Prize is nothing but Turing Award. So can you tell me, if anyone knows who was that person who got the Nobel Prize for this probabilistic models, for finding this whole theory? He used this whole theory to build up the probabilistic models. You can Google out also just now if you want. That person introduced Bayesian network. Anyone Googled out? Arey, Alan Turing nahi. No, Chandra. Turing Award given to, like, in computer science field. No, in computer science field, this Nobel Prize is called as Turing Award. Okay, named on Alan Turing only. No, that is also not correct. Julia Pearl is the correct answer. You can Google it out later on. Okay, Julia Pearl is the correct answer. So that person used this whole theory to build the probabilistic models. Okay, so we understood one thing, that cause is there and then effects are there. And given a cause, to understand what this graph is saying to us, given a cause, effects are conditional independent. One thing, given cause, effects are conditionally independent of each other. Okay, this is one thing. Other things, you can also say that the see toothache is, say toothache child cavity, so cavity is a parent, right? So similarly cavity is a parent for catch also. But how we are going to use this network to find out probabilities, we will see that in some time, okay, and in the upcoming lectures also. Let's quickly brush up our skills, in our topics for Bayes theorem. Carefully see this, we already know, but let's see this here. Probability of x comma y, that is nothing but probability of x given y into probability of y, or you can also write it like this, probability of y given x, probability of x, that we have already seen, right, in the initial part of the lecture. So I can write like this, probability of x given y, that is nothing but, so probability of x given y, that is nothing but probability of y given x into probability of x divided by probability of y. So this is nothing but, carefully see this everyone, just a minute. So carefully see this. This is what? This is posterior probability. This is posterior probability. That means some condition is there. But this is likelihood. These are the terms that they have introduced. Okay, that person introduced this term. So this is likelihood, probability of y given x. Okay, this is prior probability of x. And what is this? This is evidence. This is, if you consider this one, probability of x given y, can I say this is evidence? Yes or no? Do you agree? Probability of x given y, can I say this probability of y is an evidence? That means this has already happened. And actually you can say, when I say evidence, it is nothing but the total probability. It is nothing but the total probability, right? Or sometimes we can also say marginal likelihood. In some books you will say marginal likelihood, or evidence you can simply say. Okay, now so we can also write like this, that probability of cause given effect is equal to probability of effect given cause into probability of cause divided by probability of effect. Like this thing we have written like this. Now you just need to focus on one thing here. Don't you think that finding this probability is not easy? Probability of cause given effect compared to probability of effect given cause. When you know that this cause has already happened, then finding out the effect is easy compared to this one. Do you agree or not, everyone? You know the cause has already happened. That means you know that cavity is already there. It is given to you that cavity is there. Finding out that toothache is there or not, this is easy to find out. So I'm relating this formula to that particular Bayesian network that you have seen, the graph. So this finding this term, probability of effect given cause, is comparatively easier to find out as compared to this one, right? So when we want to find probability of cause given effect, then we use this particular formula. But one more thing is there, that this probability of y, that evidence is there, we can basically remove. So the same thing is mentioned over here also. You can just read it out, and one example is given. Yeah, so carefully see this. This is what we have. This is the other form of Bayes rule. So probability of y, I told you, right, this is the total probability. You know what is total probability? That is summation of p of y given x into p of x. Yes or no? This thing we have already covered in the previous lecture. So this thing we can write like this. Now this probability of y given x, basically this is same for all x. So what we do, we basically ignore this and we introduced one, like this is same for all x. So basically we can ignore this term and we introduce the normalizing constant over here, which is alpha, right? So basically we compute this one. Whenever we want to compute this probability of x given y, which is posterior probability, we compute the likelihood, multiply it with prior, and then whatever is the result, we simply normalize it. Why we are normalizing? Because we are removing this term, because it is same for all value of x. I hope it is clear. Okay, so posterior is directly you can proportional to likelihood multiplied prior. Is this clear? Any doubt, anyone? Yes, no, say something. Sumit, Chandana, Abhas, Manjunath, Gurdeep, Madhav Rao. Crystal clear so far? Okay. And there are some other forms also, like for conditional Bayes rule. We can write like this. So these are simply probability of x given y comma z. You can write like this. See, like if you want to just remember, easily recall what to write. So this is cause, this is effect. So what is given here? You have it like x given y comma z. So here it will be y given x comma z. So simply what you do is you just have given z in all the terms. Okay, then this thing you can just write like this. This will be your evidence. That means the total probability. You just ignore this term and you get this thing by introducing this normalizing constant. Again, the same thing is done here, nothing else. Okay, here they are talking about 3 variables, random variables. Here you just have 2 random variables. Okay. Fine. So the same thing is mentioned over here. What similar thing we have done here, probability of, by using Bayes rule and conditional independence, probability of cavity given toothache and catch can be written as, see, it has already removed that total probability, the evidence. So introduce this normalizing constant. So probability of toothache given cavity multiplied by probability of catch given cavity into probability of cavity. All these things, right? How we are finding it out, just using the conditional probability and the multiplication rule, nothing else, right? So this cavity, if you see this graph here, cavity is having this cause. Cavity is a cause which is having the effects. So when you can say given cause, effects are conditionally independent. So, and this model, this probabilistic model is nothing but your naive Bayes model that you study in machine learning. Is this clear? Okay. So this is saying that given a cause, all the effects are conditionally independent, right? So we use this concept for Bayesian network, and we have a probabilistic model for it, which we call it as naive Bayes model, which you study in machine learning, and you have already studied, right? I hope so. Clear? So this is the concept here. Now, how we are going to use this Bayesian network, how we are going to use this graph, that we are going to see in the next lecture. And we are also going to solve a previous year question that they have asked in the GATE DA exam. Okay, and we will be solving one or two more practice questions also. Okay. So after all these concepts, can I say that initially we had exponential time complexity and space also? If I talked about space complexity, we need exponential space, right, to store all the parameters in the joint distribution table. But after using Bayes rule and conditional independence, the total number of parameters is linear now in N. So if I talk about just this example, how many finally we need? How many entries we need? 5 entries we need. Yes or no? 5 entries we need. Bayes can change it to linear from exponential. Yeah, not just Bayes rule and conditional, concept of conditional independence we have used, right? If you are not using conditional independence, then you cannot reduce it to linear. So both Bayes theorem and conditional independence are used here. Is this clear? Okay, so from exponential, now the total number of parameters we need is just linear. Okay, that is your naive Bayes model. I hope you have studied this, right? In the naive Bayes model, the same thing you studied there also. Fine. So what is the summary? What is the final summary that we have discussed so far? Probability is a rigorous formalism of uncertain knowledge, right? Joint probability distribution specifies probability of every atomic event. That also we saw, right? Queries can be answered. Any queries can be answered by inference by enumeration. What does that mean? That means summing over atomic events. That means through that entire distribution, you can answer any question, right? And can reduce combinatorial explosion. That means all those like exponential time that you are taking or space you are taking. So you can reduce it by using independence and conditional independence. This is the summary of today's lecture. Is it clear? Now there are some questions, like I can give you these questions are simply based on Bayes theorem. So what do you want? Do you want these questions as homework, or should I solve this now? You can let me know. That's all for this class. Tell me, homework or we should solve it now? Homework? Okay. So let's take these questions as homework and discuss in the group. And if you have any doubt, I will tell you the answers if you want. I haven't heard these questions, Abhas. So I can tell you the answers later on. Is this clear? So you can try solving this and you can discuss in the group, okay? And if majority of you are getting the same answer, that means the answer is correct. But again, you can just tag me, I will answer the questions, okay? Yes, these are very simple questions. All these three questions are just based on the Bayes theorem. Okay, just the Bayes theorem, nothing else. Okay. So tell me, did you enjoy today's class or not? See, understanding these conditional independence, all the theory that we have covered, this was very important to build up the Bayesian network. I could have explained you Bayesian network directly. Like this is the parent, these are the childs, and this is how you solve the question. But why we are doing it? What is the intuition behind it? What is the logic behind it? Why this network came into the picture? This is the theory. Okay, great. So I hope you enjoyed it. We'll see you tomorrow. And tomorrow we will be talking about the Bayesian network. Covered initial 5 lectures of probability in 2 lectures.